Hello there and welcome. This is section 1.8. We're going to be talking about the derivative as a rate of change, which is going to mean slope. It's all about the slope. So average rate of change. Let's consider a function y equals f of x defined on the interval between a and b for my x. The average rate of change of f of x over this interval is the change in f of x divided by the length of the interval. That's just the slope. I'm going to do for the average rate of change from a to b, f of b minus f of a, which are the y values, all over b minus a. Let's look at a problem. Suppose that f of x equals negative 6 over x. What's the average rate of change of f of x over the interval 1 to 1.2? So we know what the average rate of change is. It's those two y values over the difference in the x values. So what we're going to do is we're going to plop in those values for my function. I've got the function. I can plug in those values. And plugging in those values to get the y over the difference in the x's, I'll get that slope is 5. The instantaneous rate of change, now that is the derivative right at a point. The average rate of change is over an interval, but this is that tangent line. So the derivative as instantaneous rate of change, the derivative f prime of a measures the instantaneous rate of change of f of x at x equal a. So let's look at an example. Suppose f of x is our same function, negative 6 over x. What's the instantaneous rate of change of f of x when x equals 1? Well, first off, the rate of change of f of x at x equal 1 is equal to the derivative at 1. So what we're going to do then is take the derivative, and then we're going to plop in a 1, and we get that slope is 6. That means that the rate of change is 6 units per unit change in x. All right. Average and instantaneous rate of change. Let's look at a couple of these. We're going to look at this figure below. It's a curvy line from 0 to, looks like 12, where f of t is the percent yield, which is the interest rate on a 3-month T-bill. It's a U.S. Treasury bill, T years after January 1st, 1980. So there's January 1st, 1980 at t equals 0. Here would be at t equal, let's see, that's what we say it was 12, so 92. That would be January 1st, 92 over here on this right-hand end. What's the average rate of change on this yield from January 1st, 81 to 85? So what is the average rate of change? That's just the slope. So it's the slope of the line where t equals 1 to t equals 5. So we're just going to find that slope. How fast was the percentage yield rising on January 1st, 89? That's going to be a derivative. And then C is asking me, was the percentage yield rising faster on January 1st, 1980 or January 1st, 1989? I'll just compare the slopes of the tangent lines. So here we go. A, to determine the average rate of change in the yield from January 1st, 1981 to January 1st, 1985. We're first going to have to determine the coordinates of the 2 points that correspond to the 2 given dates. That means when t equals 1, we plop in and look at that point, and that y value is 14. When t equals 5, we look at the y value, that's 7. So now all we have to do is use the average rate of change formula, which is just slope. So I'm going to do the difference in the y's over the difference in the x's, and I'm going to get negative 7 over 4. That means that the average rate of change in the yield from January 1st, 1981 to January 1st, 1985 is negative 7 over 4. To determine how fast the percentage yield was rising on January 1st, 1989, we're going to first have to determine the instantaneous rate of change of f of t when t equals 9. So we don't have a function, so that's going to be a little hard to do. So this means we're going to have to find the slope of the tangent line. So we're just going to kind of draw this tangent line, and then on the graph where we think it about is, since we don't have a function, and the tangent line on the graph, we're only going to need 2 points on that tangent line, then we'll get an estimate value of it. And using the coordinates of these 2 points, we're going to calculate the slope of the tangent line, and that's going to be the instantaneous rate of change that we're looking for. So notice that the 2 points of the tangent line that we're picking are 5, 5, and 11, 10. And notice that slope of that tangent line, looking at those 2 points at, let's see, we chose that t equals 11 and t equals 5. We got those 2 points, and we found that the average rate of at the percentage yield rising on January 1st, 1989 was 5/6, with just that slope. To determine the percentage yield rising faster on January 1st, 1980 or January 1st, 1989, we need to know the slopes of the tangent lines, and still this is an estimate here because we're just drawing these to t equals 0 and t equal 9. Although we already have the information for t equal 9, we don't have the information for t equals 0. We need to draw that tangent line to the graph at t equals 0. We did this, and notice below that is much steeper. So basically, we can say, hey, we know that the January 1st, 1980 was way steeper. So it was changing a lot faster there. Obviously, finding the coordinates of the 2 points in the tangent line might prove a little difficult because we don't really have much graph left. However, notice that the slopes of the tangent lines, that's all we're really interested in anyway, are not remotely similar. That means that tangent lines are not even close to being parallel. Therefore, in this circumstance, it'd be sufficiently appropriate to just notice that the blue line, it has a steeper slope, and therefore the rate of change on January 1st is 1980. We're going to call this an eyeballing technique, and we only use this when absolutely necessary and with great care, meaning don't do it if it's close. Average velocity. Given a position function s of t, the average velocity from t equal a to t equal a plus h is just this same slope. We're just going to be the distance traveled over the time elapsed. So it's my y values over my x values, and this plus h is just with a little bit amount. That's what that means. It means some point, but with a little bit more. So let's suppose a car is 3 miles from its starting point after 5 minutes and 7 miles from its starting point after an additional 6 minutes. And that's a total of 11 minutes. The average velocity of the car is what we're looking for. And so between those two given locations, we're going to do s of 11 minus s of 5. That's the two y values. Over the 11 minus 5, we will get that that slope is 2/3, meaning we're going 2/3 miles per minute, where a is 5 and h is 6. So we have these definitions for position, velocity, and acceleration. The definition for velocity is if s of t, which is the position, denotes the position function of an object moving in a straight line, then the velocity v of t of the object at that time t is given by v of t equals s prime of t, meaning that the velocity is equal to just the derivative of the position function. Acceleration as first derivative of velocity just means that the acceleration is just the derivative of the velocity function. And then acceleration as a second derivative of position. The acceleration function is just if you don't really have the velocity, I mean, you would because you have to take the second derivative, but just take the second derivative of the position and then you will have your acceleration function. Now, s of t is a position function, v of t is a velocity function, and a of t is the acceleration function. So if we look at a toy rocket that's going to be fired straight up in the air, there's the position function, 160t minus 16t squared feet after t seconds. We need to know the rocket's initial velocity when t is 0, and then the velocity after 2 seconds, and the acceleration when t is 3, and at what time it's going to hit the ground, and at what velocity will the rocket be traveling just as it smashes into the ground. To determine what the rocket's initial velocity is, we must first have a velocity function, and then we're going to evaluate t equals 0 at that function. Well, we've got it, and there it is. And what we're going to do is take his derivative to get the velocity function. Then we'll plop in a 0 and figure out what we have. We get v equals 160. Therefore, the initial velocity of the rocket is 160 feet per second. Next, we need to determine the velocity after 2 seconds. So we take that same velocity function that we found when we took the derivative, 160 minus 32t, and then we just plop in a 2. Computing that arithmetic, I get that the velocity at t equal 2 is 96, meaning that the velocity of the rocket after 2 seconds is 96 feet per second. Now, to determine the acceleration when t equals 3, we must first find the acceleration function. We'll already have the velocity function, so I'm just going to take its derivative and get the acceleration function. That means the acceleration is negative 32. Since the acceleration function is a constant function, the acceleration of the rocket is a constant negative 32 feet per second squared. Therefore, the acceleration when t equals 3 or whatever is negative 32 feet per second squared. To determine at what time the rocket will hit the ground, we need to determine what we know about the position, velocity, and acceleration of the rocket when it hits the ground. We know that at the time of impact, the position of the rocket will be 0 feet above ground. Yeah, it's right on the ground. Therefore, we're going to use the position function, set it equal to 0, and then we're just going to factor that and solve it. We're going to end up getting that our t equals 0 and 10. So, of course, it was on the ground at t equals 0, and then it's on the ground again at t equal 10. So at 0 feet above the ground, at times t equals 0 and t equals 10. T equals 0 corresponds to when the rocket first began its flight. So that's not really what they're looking for, but it was on the ground. So the rocket will hit the ground after t equals 10 seconds, and that is what they're looking for. To determine when the rocket will be traveling, how fast it's going to be going, what its velocity is as it hits the ground, we're first going to use the velocity function. So the question is, what do we use it for? What do we know? Well, we just need to find that when it hits the ground, we know that the time was 10 seconds. So all we have to do is just plop in a t, do the arithmetic, and the velocity is negative 160. That means that when the rocket hits the ground, it'll have a velocity of negative 160 feet per second. That means it'll be traveling 160 feet per second in the downward direction. Approximating the change in a function. Now notice this is just once again the slope. This time it's the slope of the tangent line. So we're going to have f of a plus h, or f of a plus a little bit. So let's look at our x down here, a, and then I've got my a plus h, and then this would be the y value at that point, and then that slope of that tangent line is supposed to be the change in a function, or approximate. So let's suppose 5 milligrams of a drug is injected into the bloodstream. Let f of t be the amount present in the bloodstream after t hours. We need to interpret what does f of 3 equal to 2 mean, and what does f prime of 3 equal to negative 0.5 mean. We're going to estimate the number of milligrams of the drug in the bloodstream after 3.5 hours. Well, first off, f of 3 equal 2 means that after 3 hours, 2 milligrams of the drug will still be in the bloodstream. Now, f prime of 3 equal negative 0.5 means that after 3 hours, the rate at which the amount of drug that is diminishing, because it's a minus, within the bloodstream is 1/2 of a milligram per hour. To estimate the number of milligrams in the drug in the bloodstream after 3.5 hours, we're going to use the formula f of a plus h minus f of a. That's my average change in a function. It's going to be equal to just the derivative at that value times the h. So I know that my a is 3 and my h is 1/2. So I'm just going to plug those values in, and I'm going to get that answer is then negative 0.25. F of 3.5 is 1.75. Therefore, the approximate number of milligrams of the drug in the bloodstream after 3.5 hours is 1.75. All right, well, that concludes section 1.8. If you have any questions, be sure and let me know, and y'all have a really nice day. Thank you.